Welcome to Grand Rounds today. I have the distinct pleasure of introducing Dr. Eli Adashi, who is someone who I have known for, gosh, 37 years, I guess now. Dr. Adashi, he doesn't have it on this script that he's going to say, but he was here at University of Maryland for a number of years as the division director of the Division of Reproductive Endocrinology. He is the former 5th Dean of Medicine and Biologic Sciences at Brown University. Dr. Adashi, an academic physician executive, is a graduate of Tel Aviv University School of Medicine. I'm not going to say the year, Dr. Adashi. He graduated the Harvard T.H. Chan School of Public Health program in healthcare management in 2005. So later in his career, a former president of the Society for Reproductive Endocrinologists, the Society for Gynecologic Investigation, and the American Gynecologic and Obstetrical Society. Dr. Adashi also served as examiner and director of the Division of Reproductive Endocrinology of the Board of Obstetric ABOG. Dr. Adashi, it's always great to have you here at the University of Maryland. I like to call it your old alma mater here as well. And he's going to really give us an interesting talk on in vitro gametogenesis, is how I'm pronouncing it. Is that close enough?
Correct. Yes.
All right. With that, Dr. Adashi, the floor is yours.
Thank you, Rob. And yes, it's always a pleasure to be back at the University of Maryland. Carrie knows that I've been making an effort to show up every year, once every year. And I think for the most part, we stuck with it. Here and there, we may have missed the grand round. But on the whole, I continue to feel very warmly towards the school, towards the department. The late Dr. Crenshaw, who I worked under, was a true gem. It was sad to lose him in 1994. But I tried to stay in touch with as many of the actors who were there at the time. I shared that with Carrie earlier. I should probably share this with Rob at another time. But all in all, I'm just delighted to see you and to be in a position to contribute today. The topic is indeed quite special. In vitro gametogenesis, which is not quite ready yet for prime time, is nevertheless, maybe not in all our lifetimes, but before too long, will almost certainly replace a major part of IVF. It will substitute for it in a major way. And it will allow for the first time the previously unthinkable prospect of same-sex parenting. In other words, have two men in a homosexual relationship father a child, although they'll need a surrogate, of course, to carry the pregnancy, and two women in a relationship could potentially have a child of genetically their own, as well as, of course, carry it in their case. So this will dramatically alter reproduction as we know it, which is why I think it's useful to pay attention to it. The beginning is rather modest and really dates back to Japanese investigators who made most of it happen so far. This is probably the earliest paper I could find which alluded to the possibility of creating germ cells in vitro. And the two actors that one needs to be aware of are Mitsunori Saito from Kyoto University and Katsuhiko Hayashi, who is now at Kyushu University. In 2013, I was in Japan for another reason, but I took a flight to Kyoto, at which time these two investigators were still together and working on in vitro gametogenesis. I spent a lovely hour or two with them and got the first-hand report on where they stood. And they continued to progress ever since, which of course I will share with you later today. But if credit is due, those two are probably the central actors here. They have yet to be replaced. They've been supplemented and augmented by some other investigators, but the credit really goes to these two gentlemen. We will speak today about two paradigms. The rodent paradigm, which led the way, and increasingly the human paradigm, which of course we all would be very interested in. All of this would not have been possible without the discovery of so-called pluripotent stem cells, also known as embryonic or induced stem cells. These are incredibly flexible cells that can essentially become any cell in a body. You could, in principle, create amacrine neurons that could be placed in the retina in individuals who may be lacking those. You could imagine creating dopaminergic neurons and maybe implanting them in the striatum in patients with Parkinson's disease, for example. Or you could create motor neurons and imagine perhaps a paralyzed individual walking again, all of which is unimaginable and at this point still theoretical, but in principle, I think doable and will likely happen in some fashion or another. But what we will speak about today is, of course, stem cell-derived gametes, which is a subsection of this large area of pluripotent stem cell technology. Now, if we are to produce gametes, those gametes would have to have the correct nuclear DNA content. They would have to have the normal chromosome content and organization. They would have to display appropriate synapses and recombination, and obviously give rise to a viable euploid offspring. Science Journal understood the significance of in vitro gametogenesis and dedicated a significant spread to this topic in 2021. The New England Journal of Medicine, not to be outdone, commissioned a paper in 2022 from Doctors Herbert and Surani titled Oocytes from Stem Cells and published it in 2022. And the National Academy of Medicine convened a workshop last year, and a consensus committee report may well follow before too long. It is also interesting to see what the Nuffield Council on Bioethics in the UK thinks about in vitro gametogenesis. As you know, the Nuffield Council is the prime ethical organization, ethics organization in the United States, which is very interested in reproduction. When they spell out in this infographic what they are going to study under the human reproduction rubric, they start off by mentioning in vitro derived gametes. And then they go on to discuss time limits on maintaining embryos in culture, womb replacements, that is to say, artificial wombs, preconception screening, whole genome sequencing of embryos and fetuses, genome editing of gametes and embryos, and egg freezing. But at the top of the list, you couldn't have helped but note that they mentioned in vitro gametogenesis. This is by definition a disruptive technology. It will change science and life as we knew it. It still remains to be documented unequivocally that it is achievable in the human. And the timeline, we have to admit, is still somewhat uncertain. It is always good to reflect back on the work of Aldous Huxley, Brave New World, which was published in 1932, in which he made several key predictions. He suggested that eggs would be produced via ex vivo ovarian cultures, that embryos will be produced via in vitro fertilization, and that newborns will be born via ex vivo ectogenesis. In a word, he predicted in many ways in vitro gametogenesis, he predicted in vitro fertilization, and he predicted artificial uteri, if you will, which all of which is progressing in its own pace with different investigators and different realms of science. But he was definitely right on when it comes to IVF, which is a reality today, but in my view will be largely replaced by in vitro gametogenesis in due course. And as I said, the technology will also allow same-sex couples for the first time to constitute genetic parents of their offspring. In chapter 1 of Brave New World, the author writes, one egg, one adult, normality, making 96 human beings grow where only one grew before progress. Of course, with in vitro gametogenesis, that's exactly what we have, an unlimited number of gametes that can be produced in vitro. And in many ways, although it's not a direct quote of the author, it does approximate those predictions. Now, this is not going to be simple, and there are clearly some obstacles. Originally, the thinking was that this will never be possible, and that was because of the pervasive influence of the so-called soma germline barrier hypothesis, which was promulgated by August Weismann, professor of zoology at the University of Freiburg, who argued that case in his book, The Germplasm, A Theory of Heredity, which was published in 1893. Therein, he argued correctly that the germline gives rise to the soma, which by definition is immortal, and that the soma, in turn, gives rise to the germline, which would be mortal. But the conclusion was that this particular development is unlikely to be reduplicated in the form of in vitro gametogenesis. But then came pluripotent stem cells and the technologies that make them possible. And the first technology that made them possible is known as somatic cell nuclear transfer, which was introduced in 1958 by John Garden from Cambridge University, who reported in a Nature paper, using frogs in this case, that if you start with a somatic karyotype, combine that with an oocytic cytoplasm, you create effectively a zygote, which goes on to develop into a blastocyst, give rise to an inner cell mass, and from which you can then harvest embryonic stem cells. Later on in 2006, another technology known as induction was introduced by Shinya Yamanaka, MD, PhD, a professor at Kyoto University, whose first paper was published in Cell, titled Induction of Pluripotent Stem Cells for Mouse Embryonic and Adult Fibroblast Cultures by Defined Factors. He started with somatic cells, let's say a skin cell. He transfected that cell with select transcription factors, and voila, he produced induced pluripotent stem cells. Both gentlemen appropriately were the recipients of the 2012 Nobel Prize in Physiology and Medicine. So in vitro gametogenesis, as we think of it today, involves starting with a somatic cell, whether it's from a buccal smear or from a skin biopsy, converting that cell either to an embryonic or an induced pluripotent stem cell, more likely an induced pluripotent stem cell, and then guiding that pluripotent stem cell towards a gametogenic fate. Now, that's simple to say, but what are the prerequisites of guiding a pluripotent stem cell towards a gametogenic fate? Well, you need to know the germ cell specification pathway. You need to know the cues that have to be applied. You need to know the sequence by which they are applied, the timing thereof, and you have to take into account the presence of a niche, which, as you know, in the ovary is represented by the granulosa and theca cells, and in the testes is represented by the Sertoli cells. And so it's hardly a simple sequence, but in principle, those are the things you would have to master to accomplish the goal. The beginning was modest. Perhaps the first paper that ever demonstrated, and in fact showed a photograph of an oocyte that was derived, in this case, from a mouse embryonic stem cell, was Hans Schöller, who at the time was a postdoc at the University of Pennsylvania, but today is the director of the Max Planck Institute for Molecular Biomedicine in Germany. He published a paper in Science wherein the possibility of deriving oocytes from mouse embryonic stem cells was reported for the very first time. That same year, Toshiaki Noche from Japan published a similar paper on the pages of the Proceedings of the National Academy of Science, titled Embryonic Stem Cells Can Form Germ Cells in Vitro. And George Daly, currently the dean of Harvard Medical School, published in Nature in 2004 a paper titled Derivation of Embryonic Germ Cells and Male Gametes from Embryonic Stem Cells. Finally, René Pera, then at UCSF, published a paper in Human Molecular Genetics titled Spontaneous Differentiation of Germ Cells from Human Embryonic Stem Cells in Vitro. During the decade between 2000 and 2010 and eventually 2020, a series of leading papers saw press. This is a sample of papers that dealt with the issue in the rodent. A similar series of papers dealt with the issue in the human. And so by the time we arrive at around 2015, the state of the art was that we knew that the germ cell specification pathway is not conserved between the rodent and the human, which meant we had to do some extra work to figure it out, and that the genetic networks involved are quite distinct as well. In other words, a human is not a rodent, and the mechanics of it all are clearly quite different. So at that point, we probably understood what was meant by stem cells, be they embryonic stem cells or induced pluripotent stem cells. we probably knew how to transform those to so-called primordial germ cell-like cells, a process that in vivo transpired in the extragonadal compartment. What we didn't really know was how to take those primordial germ cell-like cells and take them all the way to haploid postmeiotic mature gametes, a process that normally in vivo occurs intragonadally. So we knew how to do it extragonadally. We had to master the intragonadal pathway. And so the final frontier was what I call in vitro gametogenesis all the way. And that's really where we are today. In the rodent, the first demonstration of this possibility was provided by the now familiar Katsuhiko Hayashi. That occurred in 2016 and was reported on the pages of Nature. He reported the reconstitution in vitro of the entire cycle of the mouse female germline. He started with embryonic stem cells or induced pluripotent stem cells, converted them to so-called primordial germ cell-like cells, combined them with gonadal somatic cells, produced primary oocytes, eventually M2 oocytes, an image of which is shown on the left lower hand side, fertilized those eggs, created an embryo and a blastocyst, and eventually gave rise to pups. So this was the first demonstration that you could take an induced pluripotent stem cell or an embryonic stem cell in the rodent anyway, and take it all the way to pups, which gave rise, of course, to the hope that some of the same could be reproduced in the human. To show the prowess of these investigators, I'm simply sharing the fact that since he was lacking at that point the appropriate somatic cells, Hayashi went on to produce ovarian follicles from mouse pluripotent stem cells as well. This was almost a side project, but he published that work in Science. And so we can produce, of course, any cell type from induced pluripotent stem cells. And he saw to it that not only are we producing gametes, but we also are producing the somatic cells that surround them. On the male side, Michinori Saito, in a paper in Cell Stem Cell, showed the in vitro reconstitution of the whole male germ cell development from mouse pluripotent stem cells. Again, he starts with embryonic stem cells and ends up with round spermatid-like cells. And so in the rodent, I think we can feel reasonably confident that we have the recipe and the insight to take pluripotent stem cells, be it induced or embryonic, and take it all the way to a functional gamete that is capable of fertilizing and, in principle, producing offspring. Things, as I said earlier, are more complicated and less advanced in the human paradigm. Here again, however, our friends from Japan, Professor Saito in this case, reported on the pages of Science the generation of human oogonia, not M2 oocytes, but oogonia, from induced pluripotent stem cells in vitro. He started with human primordial germ cell-like cells, combined them with somatic cells, and took those cells all the way to oogonia, but he could not, at that point, reach the stage of M2 oocytes, which is what it would take if we wanted to proceed to fertilize and derive an offspring. In other words, the pathway in the human has only been partially recreated. Some of the same can be said about the human spermatogenic pathway. In this case, Kotaro Sasaki, who is a faculty at the University of Pennsylvania, reported the reconstitution of prospermatogonial cells in vitro from human-induced pluripotent stem cells. So again, he came along quite far along the pathway, but didn't quite get to the end of the line with a human counterpart. And the question then becomes, of course, when and if are we going to be in a position to produce human M2 oocytes and human spermatozoa that are capable of fertilization and the creation of viable offspring? So human in vitro gametogenesis obviously will require the support of granulosa cells, theca cells, and in the testes of Sertoli cells. And just so we are not in short supply of those, George Church from Harvard Medical School has recently reported on the pages of eLife the generation of human granulosa cells from induced pluripotent stem cells, which overcomes at least one of the shortcomings or one of the gaps in our ability to have a human system to produce human gametes. Now, you can all appreciate that when and if we, in fact, are successful in taking human in vitro gametogenesis to its ultimate logical conclusion, there will be a significant scientific and translational promise. In terms of advancing science, we will, for the first time, have an inexhaustible supply of germ cells. We will be able to subject those to functional analysis. We could study, to our heart's delight, germ-somatic cell interactions. But there are also clinical benefits here, which are just as important, if not more important. We could, in principle, reverse germ cell failure by autologous gamete replacement, perhaps when necessary, gene-edited gamete replacement, and of course, donor mitochondrial replacement would become enhanced as well. I also foresee a significant impact on IVF. We may not need to stimulate women to produce eggs, which will ultimately be surgically removed. We could do away potentially with gamete donation and perhaps with the age-dependent issue that is currently plaguing some individuals. In essence, we would convert IVF to a laboratory procedure. We would still require endometrial preparation and embryo transfer, but everything that precedes it could potentially be bypassed. Would that improve affordability and thus access, in that we know that IVF does not come cheaply? I would put a question mark there because we've been there before. We always express the hope that clinical care will become more affordable, but we've also been repeatedly disappointed to find out that in reality, this doesn't really happen. But the enterprise of IVF, which is now a substantial one, in my view, over time, will have to change and adapt dramatically to a point that it will probably no longer approximate what we currently know as the IVF enterprise. Needless to say, this will require regulation. And thankfully, we have the FDA jurisdiction to ensure that the gametes that are produced by in vitro gametogenesis are safe and credible in every way. I often like to say that the FDA is the last thing between us and another thalidomide affair, and I mean it wholeheartedly. I think this is an exceptionally important institution, and it will have to be applied in this context. The likelihood is that the Center for Biologics Evaluation and Research, which is led by Peter Marks, MD, PhD today, will likely be the place where artificial gametes are going to be assessed and approved by the FDA. In the lingo of the FDA, the artificial gametes will be known as HCTPs, or as they refer to it, as human cells, tissues, and products. But the infrastructure to assess artificial human gametes is in place and thankfully is available and will be there to be sure that whatever we proceed with is safe. I will conclude with this slide of the Nuffield Council on Bioethics, which, in my view, saw the future correctly by placing in vitro gametes at the top of the list. Only time will tell, of course, if any of us is correct. But my sense is that this is a life-changing technology, a science-changing technology, a discipline-changing technology. It will alter what we currently think of is a reproductive endocrinologist and the practice thereof. And so we will do well to pay close attention to where this field proceeds, because it is not a minor modification of what we do. It is a sea change that will definitely be there to define what it means to have a reproductive process. So stay tuned. Thank you very kindly for your attention throughout. I hope this came through clearly, but I'm more than happy, of course, to entertain any questions. So thank you very much again.
Thank you so much, Dr. Dashi. What a fascinating thought as to where our reproductive endocrinologists could be going. And really, I mean, you take away really the whole role of our RAI physicians and put it all in the lab. You know, it's really quite fascinating. I'm going to open this up for questions from the audience. Maybe I can start with Dr. Giacherny or Dr. Reese.
Yeah, I have a question.
Sure.
If you grow oocytes from buccal mucosa from a 60-year-old woman, what will those be normal oocytes?
No, I mean, I would be worried. And that's why almost the very first slide I showed tried to illustrate what the Jackson Laboratory, in this case, expects from a normal oocyte. And so I definitely wouldn't recommend a 60-year-old subject as a studying material. Having said that, I try to be open-minded, Alan, and not to close on any possibilities. This will take probably a longer discussion as to why a 60-year-old individual would even consider this possibility, but I don't want to close it up and or be determinative or somehow close-minded about it. But in principle, I think you would want to work with material that is less liable to chromosomal alterations and other aging-related processes that we may not even be aware of, that definitely cast doubt on oocytes from a 60-year-old as opposed to an oocyte from an individual in the reproductive age range.
Well, the essence of the question is that cells have internal clocks. And does growing cells from stem cells, does that negate the fact that these cells have internal clocks that actually lead to apoptosis?
That is true. And perhaps the first thing we should say is the experiment would have to be done to even be able to say anything meaningful about it. But speculating as I do, without any data to back it up, common sense suggests that this is probably not an area we want to turn to first. And in general, be very careful and thoughtful before we embark on anything along these lines.
So, Ellie, let me just say, first of all, outstanding science.
Yeah.
It reminds me of the whole era of synthetic biology,
Yes.
where you're basically producing new life from a very nascent start. And I wondered while you're talking, I began thinking that, and I want you to edit what I just said, what I'm going to say, because I'm not sure I'm correct, but my mind began to wander. Since one could, in theory, produce an offspring from a single person, because the induced pluripotential cells could come from, as Alan said, a buccal smear, or basically a skin cell. But since it's pluripotential, the spermatogonia could also come from that same person's induced pluripotential cell. And if they are guided along the various developmental pathways, they can develop into, on the one hand, the sperm, on the other hand, the oocyte, and go along. Is that following the logic that you described? Would that not be a potential conclusion that you really don't need two people, just need one? Is that correct or not?
I think it is correct in principle. I would add, or hasten to add, that has not been attempted either in the rodent, let alone in the human. And by that I mean in vitro.
Yeah.
At this point. But I would say, in principle, for example, if you start with with a male germ cell, skin cell, for example, you could, in theory, produce X-bearing cells and Y-bearing cells.
Mm-hmm.
And yes, in theory, all of that is possible. Nobody really has considered that possibility, although the notion of same-sex parenting has now received a great deal of attention, and appropriately so. I'm talking about same-sex genetic parenting, which I think for the first time is approximating a point where it might be a reality. But nobody has gone as far as you have just proposed, which is not to say that it's infeasible. And neither you and I probably want to get into the question whether it is desirable or appropriate or in any other way useful. But since we're talking rather inventive gymnastics here, it's almost at the point where almost nothing is impossible.
I think that at the very least, from a conceptual standpoint, that is a possibility. But also, just with synthetic biology, creating a cell from nothing, almost nothing, in the same way. So science, the frontiers of science are clearly moving. We're not there yet, but it's certainly moving quite rapidly.
And they are raising, just like your question, ethical questions and notions of practicality and common sense. In other words, just because we can do it, does it mean we should? And I think that's where some wise men and women will have to weigh in as this technology proceeds. But I think as far as I can tell, and by the way, those of you who follow this more closely, just last week, Nature magazine carried a paper from the Oregon group, headed by Dr. Mitalipov, which reported a relatively simple way of producing an in vitro gamete in ways that simplify the process substantially compared to what I described heretofore. In other words, this is a moving front, a rapidly moving front that we must keep a close eye on. I think it's high time that the National Academy went beyond a workshop and produced a consensus report. I don't see that happening. Part of it is lack of money, but I think part of it is also a more contextual, I think, absent of decision on that particular issue. But this is happening relatively quickly. And as I said, just this last week, new technologies have been introduced that further simplify the process. And so we all need to keep a close eye on it. It's that simple.
So Al's question is interesting because on one hand, it sounds like it's just cloning by a different pathway. But on the other hand, it looks like because of the integration of the two gametes, the risk of genetic malfeasance is tremendous.
Definitely. I mean, that said, I mean, nature is replete with self-fertilizing organisms. I mean, the notion of self-fertilization is not foreign, but it has not been part of human cultures since we all started with Adam and Eve. And it was Adam and Eve who obviously defined how the rest followed. So to us, meaning humans, the notion of self-fertilization, if I can call it that, is really a new and unforeseen notion, which has not been dealt with in the past. But there's nothing wrong with discussing it, nothing wrong with thinking it through, and nothing through with pointing out the ups and downs of it.
The egotist dream.
Well, that's one way of thinking about it.
Are there any more questions or discussion for Dr. Adachi? Well, it certainly seems that there's a lot of work to be done. It certainly is going to take a lot of work from our ethicists and certainly our geneticists if it comes to reproduction by self. all those recessive disorders could come through quite a bit if we head that way. So we have a little bit of time so people can get themselves prepared for the next hour. Dr. Adachi, it's been a pleasure again to have you, and we look forward to seeing you next year. And it's a pleasure to have Dr. Reese and Dr. DeCherney. People who don't know these two individuals should look them up and see the great work that they have done over their careers in not only reproductive endocrinology, but maternal fetal medicine as well. So thank you both for being here as well to help with our discussion. Everyone have a wonderful day, and we'll see you again.
Thank
Take
you
care.
so much,
Bye.
Rob.
Bye, everyone.
Thank
Bye-bye.
you, Dr. Adachi.
Thank you
Thank
so
you.
much.